Welcome back. This will be the last lecture of week 5. We are going to uh, continue with logic coverage criteria. We learned all the theory, the basics of logic, the definitions of coverage criteria, how to make a clause determine a predicate. Now we'll take a break from that and apply all that we've learned there to test actual code. So I'll teach you two examples and one in the next in this lecture, one in the next lecture. So just to recap what we saw, we know that logical predicates are available plenty in source code. Typically, any code that we write in a typical programming language has decision statements. By decision statements, I mean things like these: if, with or without, the else, switch case statements, while do while, for loops, repeat, until. So many different flavors of decision statements. All of them will have a logical predicate in them that will eventually return true or false, on which we could apply the logic coverage criteria that we learned to test out. Typically, theoretically, a logical predicate can have as many clauses as possible. Some very complex control logic, in fact, have large predicates with many clauses. But typically, most programs have predicates that contain maybe two, three, or four clauses, not dozens of them, except in rare cases. Sometimes many programs just contain only one clause. The entire predicate is just one clause, in which case, almost all that we learned in terms of clause coverage, active clause coverage, the three subsets, inactive clause coverage, all that becomes one and the same as predicate coverage. Things begin to look interesting if a predicate has a logical operator and two or more clauses connected by the logical operator. So when we try to apply logic criteria to program source code, it's not as simple as just going to an if statement, somehow parsing the logical predicate in that if statement, extracting it, and then using the logical coverage criteria. There are several problems that we have to solve. First is reaching that particular place. Let's say you have a few thousand lines of source code, and that logical predicate is a few hundred lines away. And to reach that, you might have to test a few of the predicates before that, true and false, based on the path that it takes. Maybe it also involves a few function calls. So, reaching that particular decision statement containing the logical predicate that you want to test can be challenging. How do I give test input such that I can reach that statement? The next is, once I've reached the statements, I need to be able to do my clause coverage, correlated active clause coverage, inactive clause coverage. So I need to find test inputs, which are going to be as inputs that will be able to exercise different logical coverage criteria on these predicates. So that is controllability. The predicates could be such that they will all have internal variables, variables that are local to the method or the procedure, and may not have, or not all those internal variables will be test inputs. So we'll have to rewrite the internal variables in terms of test inputs and get newer logical predicates. So the problem of controllability needs to be solved. And sometimes the variables can get redefined along the way as you reach a particular statement. So those definitions that occur of a variable along the way have to be considered. So we'll illustrate all these concepts using two examples, one in this lecture, one in next lecture. We'll continue by looking at other applications of logic-based testing in specifications and so on. And then in the next week, I will teach you a technique called symbolic execution, which will be useful to solve these problems of reachability and controllability. So the two examples that we are looking for are derived from the textbook that we've been following mostly. One is the program for a thermostat. The other is a standard program that you will find not only in this textbook but many other software testing textbook, which is a simple high school thing that we learn, which is the program to check the type of a triangle. So we'll see the thermostat one today in this lecture, and the type of the triangle as the first lecture of next week. So what is a thermostat? I hope you all know what it is. So basically, let's say if you live in a place where the temperatures vary a lot, it can get too cold or it can get too hot. Then your house has some centralized heating and ventilation and air conditioning system. So it uses a device called a thermostat, which will switch on and switch off the heater in the room based on the temperature that is currently there and the desired ambient temperature that the person living in that room has. So this is a small Java program that gives you how to program a thermostat, and it's not a long program, but it has a very interesting logical predicate. And our goal is to understand how to test this method program using logic-based testing that we understand. So we'll first understand the code. This is a program, as I told you, written by the authors of the textbook that we've been following. Then read these dot 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 as some amount of statements that for now we don't worry about. It does exception handling and stuff like that. I'll upload the full code separately in the folder for your reference. So now let's look at this thermostat. So see the number of variables it deals with. Current temperature, which is the temperature reading of the room where the thermostat is located, where it's supposed to control the temperature. Then threshold difference, which gives you the difference in temperature until the heater is on. Maybe you desire the temperature in your room to be, let's say, 25 degrees centigrade, but you are able to tolerate a small threshold of 1 or 2 degrees centigrade. So you set that there. Then you also keep track of time since last run, which gives you the time since the heater or the thermostat was last switched off. Then what is the minimum waiting time, which is given as min lag. Sometimes the user can override this programmable thermostat by setting an override flag. So that's a Boolean variable. And when the user sets the override flag, the user manually sets the temperature also. So the temperature given by the user is called over temperature, short for override mode is on, and the user wants to set the temperature. Then there's something called runtime. You can say how long to keep the heater on after the thermostat turns on the heater. And another flag which represents whether the heater is on or not. Then some variables that talk about time and date. So period which talks about whether it's morning or evening and so on. Day which talks about whether it's a weekday or a weekend. Assume that it's a weekday, then many people might be leaving the home. Maybe you turn on the heater less. On weekends you might have to run it for long because everybody is at home and so on. So these are the variables. And thermostat is basically a small device which can be programmed to turn on or turn off the heater in a room based on the ambient temperature setting. So just to repeat, when the user decides to turn on, thermostat can read the current temperature, take input as some threshold, then it uses a whole set of these variables. In particular, thermostat can be overridden and manually operated by a user who sets on an overridden temperature. User can set how long to turn on the thermostat and so on. Okay, so here is the main code. So turn heater on is the method which takes some preset of program settings which is given in this variable called pset. So first it says dtemp. So please note this variable dtemp is local to this method, turn heater on. These are all variables that were outside this method that belong to the class called thermostat. Then we now are writing the code for the method turn heater on, which takes parameters as pset, and it has in addition a local variable called dtemp. What does dtemp do? Dtemp basically uses this pset input and pulls out period and day. Then there is an if statement which reads like this. So it says if current temperature is less than dtemp, read it as desired temp, short form for desired temp. Current temperature is less than desired temperature minus the threshold difference that you can tolerate, or override mode is on and current temperature is less than the overridden temperature minus the threshold difference that you can tolerate, and the time since the last time the heater was on is greater than the minimum lag time, then you turn on the heater and you also say how long to turn it on. So this code from lines 33 to 38 does that job. So it first says time needed is current temperature minus dtemp, And if override is on, then you please compute time needed as current temperature minus overridden temp. Then you set the runtime as this time needed, turn the heater on, and return true to say that I have turned the heater on. If you can't do this, that is, if this if condition fails in lines 28, 29, and 30, then you say I can't set the heater on, set it to false, and return false. Is this clear? Our focus is now to test this class, this method, using logic based coverage criteria. And there is one decision statement here in line 28, which is this large decision statement. And if you carefully notice, there's one more here in line 34, which involves the single Boolean variable override. Remember, override was a Boolean variable. So if statement in line 34 directly involves this override. This if statement is long. So in lines 28 to 30, I'm just recopying the if statement here. If current temperature is less than the desired temperature minus the threshold difference, or if override mode is on and the current temperature is less than the overridden temperature minus the threshold difference, and time since last run is greater than min lag, that's one if statement that was present here. Second if statement is present in line number 34, override. So we would like to take these two as predicates that are present in the program and apply logic based coverage criteria to test the program. So this looks like long thing to read, right? And if you remember in the last lectures, we learned it as clause A, clause B, clause C. So let's substitute and rewrite it just for convenience of reading. So let's assign. So how many clauses are there? Clauses are those that don't have logical operators. So if you see this first predicate here, this first part is a clause. Current temperature is less than desired temperature minus threshold difference. So let's call that clause A. Then there is an or here, and then there is one single clause override, which is itself a Boolean variable. So let's call that clause B. Then similarly, there is an and here followed by a third clause. Current temperature is less than overridden temperature minus threshold difference. Let's call that clause C. Clause D is time since last run is greater than minimum lag. So I just do some substitution. Take the four clauses that were there in this long predicate, assign them names A, B, C, and D. Now I can write the predicate in lines 28 to 33 as P, let's say P, call it P, like this: A, or B and C and D. Here I've used the programming notations for or and and. In the last few lectures, we had used the logical notations for or and and. They are one and the same. So this program has two predicates. The first one, which we are now calling it as predicate P, occurs in lines 28, 29, and 30. It has four clauses, A, B, and C, and D, which are like this. And the predicate is A, or B and C, and D. The program also has a second decision statement here at line 34, which we now have called it as B because it is just override. So that's line number 34, predicate B. Is this clear? We want to apply logic based coverage criteria to these two predicates. Now let's look at these clauses. If you see, go back here, this program has so many global variables, the main variables, right? And as I told you, turn heater on is a method which is called with this pset. And this has a local variable dtemp, right? This has a local variable dtemp. So now we have to solve for dtemp. Clause A has an internal variable dtemp. We have to solve for dtemp. What was dtemp? Let's go and look at line number 26. Dtemp is program setting, get set, period, and day. So let's solve for it. Dtemp line 26 says pset, get setting, period, and day. So set something. Let's say period is morning, day type is weekday, and temperature is 69 in Fahrenheit. So you say set period is morning, day type is weekday. Now you substitute for clauses A, B, and C. The rest of them were actual values, A, B, and C. So A was this current temperature is less than D temp minus threshold. B was override. A involved this local variable which we just solved. C was current temperature less than overridden temperature minus threshold difference. D was time since last run greater than min lag. So I just substitute. So I take predicate coverage. Look at the title of the slide. It says predicate coverage. The predicate P is true and the predicate P is false. Here are test cases for the predicate coverage being true. So what does the predicate look like? The predicate looks like, yeah, so these four variables were there and the predicate was A or B and C and D, right? So there's an and. So for this whole predicate, for predicate coverage to be true, D should be true, B and C should be true, A can be true or false. The option is with us. So that's what is given here. Predicate coverage for P being true, definitely B, C, and D must be true. A can be true or false. Here we've set A to be true. So A was what? Current temperature is less than desired temperature minus threshold difference. So assign values. Current temperature value should be less than this difference. Override should be assigned true. Similarly, for C to be true, the value assigned for current temperature should be less than this and override should be true and so on. So here are some set of values that you can assign. So it says setting is morning, day type is weekday, temperature 69. Then set period, set day, current temperature 63, threshold difference becomes 5, override is true, overridden temperature 7, minimum lag is 10, and so on. And then you write assert true. So this is like the test case that will test for predicate being true. Is this clear? Similarly, you can do for test case for predicate being false, which I have not given here. But let's move on. And for the same predicate P, this predicate P, A or B and C and D, let's do clause coverage. Okay, CSCC for P. So the same thing. You remember last time we have to determine PA. So set A to be true, XOR with set A to be false, substitute and simplify. So in the predicate P, set A to be true. So it's true or B and C and D. In the predicate P, set A to be false. So it's false or B and C and D. XOR these two. Use the laws of logic, simplify true and D, B and C and D. Go on simplifying. You can stop if you're not clear. Like for example, the third last line is also good enough. As long as you can write the truth table, assign true, false values, you need not get it to the most simplified form. So the conditions under which, if A is the major clause, A will determine the predicate P is not B or not C and D. Similarly, we can determine conditions under which B will be the major clause, PB, PC and PD, which would be C being the major clause and D being the major clause. I have not shown the working out here. I request you all to please work it out. I am now moving on with A being the major clause, B being the major clause, C and D directly. I have assumed that you will be able to work out PC, PB and PD for your own benefit using this value of P and using this algorithm. This is the test requirement for correlated active clause coverage criteria for four different clauses in turn taking to be the major clause A, B, C and D. So here earlier I had used the bold versus non-bold. Here the convention is T and F in capital letters and T and F in small letters, lowercase letters, both represent true and false. But if I distinguish them in capital letters, then this is the part where A is the major clause. So in the first case, PA, with A being the major clause, A is true ones, A is false ones. For correlated active clause coverage criteria, if you work it out, you can assign B, C and D to be true, false and true respectively. Similarly, when B is the major clause and PB is the conditions under which B determines the predicate, the column for B becomes true once and false once. And I have assigned A false, C true and D true. Any other combination might also work. In fact, they are assigned the same values. So it looks like RACC also, but any other combination for CACC will also work. Similarly, for C being the major clause, becomes true once and false once. Clauses A, B and D take false, true and true. For D being the major clause, D becomes true once and false once. Clauses A, B and C all stay as true. Then you do the usual check of pruning the test cases, avoiding duplicates. Here row number 3 and row number 5 are one and the same. So merge them and then you will need 6 test cases for correlated active clause coverage for the predicate P where each clause takes turn to be the major clause. This will involve some work, which I've skipped. I hope that you will be able to complete. So you have to determine PB, PC, PD, write out the truth table, identify these rows, and this final table will summarize the test requirements for CACC for the predicate P. Now I'm going to assign test cases. So these are my true false values. A was actually this clause, current temperature is less than desired temperature minus threshold difference. So assign values. Similarly, for A false, assign some set of values. For desired temperature, you have to substitute and then assign values. B was just the Boolean variable override, can be made true or false. For C, also assign values. For D, also assign values. Now you have these values assigned. Now write the test cases. You remember here, I'm copying these rows here. A true, B true, C false, D true. So that's what is copied here. First case, A true, B true, C false, D true. I haven't written A, B, C, D. I have directly written T, T, F, T to represent the true, false values of A, B, C, and D in order. And this is the test case for that. Similarly, second row, this is the test case. Third row, this is the test case. Fourth row, this is the test case. So on. Fifth row, sixth row. Now you have the test cases and you can exercise and get ready. So now one important thing that I would like you to remember is we took this predicate, we solved it using the algorithm, we wrote this table, and when we came here, I told you, okay, A is true, A is false, assign values. Current temperature should be some value less than desired temperature minus threshold difference. This was a small enough example. All these current temperature and threshold difference were inputs. Desired temperature was a local variable. So we could, let's assume we know the domain, we could assign values. In general, you can't scale it up. If you have a large program with several thousand lines of code and let's say a few dozen variables, you may not know how to assign values, right? So you need some automatic way of assigning values wherever possible such that the clause becomes true and the clause becomes false. So for that, we use what we call SAT solvers or SMT solvers, which are a bag of tools that will solve these kinds of logical predicates and give you values. The problem in general is difficult, as I told you in the first lecture in logic, but wherever possible, we can solve and get values. So that will be the last module that I will teach, a module on SAT solvers. For our assignments, we will look at small programs. So you could manually solve and get values. But if you're scaling it up for testing large programs, to automatically get values, you need to be able to use a SAT solver. So this was the first example. In the next lecture, I will talk about types of triangle, which would be your second example. I'll stop here for now. Thank you.